Okay, so hello everyone, I'm Yunsheng Tian. I'm presenting AutoOED, which is an automated optimal experimental design platform with data and time-efficient multi-objective organization. This is a joint work with Mina, Chen, Mike, Tim, and Wojciech from the Computational Design Fabrication Group. This paper is currently under review and the author order is not finalized, but we have a slightly outdated archive version. So optimal experiment design is a process that a scientist is trying to find the optimal choice of the next experiment to test with respect to certain performance criteria. But people will usually rely on their intuition to do so, which is problematic because our experiments might be very expensive in terms of time or money to test. So we cannot really afford many bad decisions. Therefore, our platform relies on a optimization algorithm that automates the optimal experimental design problem with the minimal number of experiments performed. So the problem setup is we have a multidimensional design space and a performance space. We want to find the optimal Pareto set, which is optimal Pareto design, optimal designs with like different trade-offs between those different objectives. But the constraints are like the evaluation function is black box, and also each evaluation is very expensive to perform. So the total number of evaluation is limited to a few dozens or a few hundreds of examples. So the key question is how to wisely select which set of designs to evaluate. This setup is quite general to many different applications, and we propose a general purpose optimal experimental design platform with a lot of nice features, including an intuitive GUI, a modular code base, and some like advanced optimization techniques. So the overall workflow is designed to like user-only interface with the GUI without the need of touching the backend algorithm or scheduling of experiments. And the fundamental data efficiency of our platform comes from the concept of multi-objective Bayesian organization, which is an iterative process consisting of first by fitting a surrogate model based on a current data set, and then defining an acquisition function that traces off the exploration exploitation, then using the chip multi-objective solver to approximate the Pareto set, and finally use a selection scheme to propose a batch of designs to evaluate next on the real-world problem. So this framework is implemented in a highly modular way in our code base, and we support many state-of-the-art algorithms, and also we allow easy customization of new algorithms. So besides data efficiency, the time efficiency is also very important, especially when the parallel experiment setup can be applied. But the key question is when we are trying to optimize for new samples, how to leverage the information of the design being evaluated. So we propose a normal strategy that leverages the confidence of surrogate model that trusts the prediction with high confidence, but penalize around designs with low confidence. So we observe a superior performance with respect to naive method and synchronous alternatives. And also we compare with existing optimization platforms, both qualitatively and quantitatively, and we observe like great efficiency, high dimensional problems. And finally, we demonstrate our real-world applicability through a PID heater controller optimization problem, and we believe this platform can be also applied to many other real-world use cases. Okay, thank you.
Hi, I'm Matthias Hofer. I'm a graduate student in Brain and Cognitive Sciences, where I'm advised by Roger Levy and Josh Tenbaum. And today I'll be talking about joint work with them and also Tuan and Lei, titled Learning Evolve Combinatorial Symbols with a neuro-symbolic generative model. So as a bit of background, I want to start out with the observation that combinatorial systems such as handwritten characters, sign language phonology, or musical notation are really ubiquitous in human culture. And the key to those systems is really that smaller meaningless units such as strokes, gestures, or musical notes combine into an infinite repertoire of larger structures that can be assigned different functions within those systems. And people are very adept at learning those systems and productively using them to generate new instances within the systems. So the kind of key questions that drive my work are how people do that. How do people learn these systems, and how do they evolve in the first place? And one, apologies for the rendering mistake here. One sort of like domain we use to study this is within an experimental paradigm called iterated learning, which is similar to the children's game Telephone, if anybody knows that. So here in this paradigm, participants learn repertoires of simple auditory signals. So here in our work, we're using signals produced by a slide whistle instrument. So I'm showing you pitch over time here in those signals. And so a single participant would learn these and subsequently reproduce them and then pass them on to the next participant and so on. So the output of one participant becomes the input for the next participant. And what we find in this process is that merely by passing through such a learning bottleneck repeatedly, these systems spontaneously develop combinatorial structure akin to a sort of phonological code. And we will use these languages here at different stages of the evolution as a data set for subsequent modeling. To understand how participants learn individual signals and repertoires of signals, we developed a hybrid neuro-symbolic model that uses neural components, both in a generative model to capture low-level statistics of the input, and in a recognition model to learn a fast mapping from input to latent variables for inference. The key to this model is the assumption that signals can be understood as a sequence of symbolic building blocks. And this model is then compared to several neural network baselines, such as an LSTM and transformer model that lack any such symbolic components. Baselines in our model are evaluated in 3 different tasks: classifying different instances of the same signal, classifying signals as belonging to a given language, and producing plausible reproductions of individual signals. And here I'm showing you ground truth. Our results show that our neuro-symbolic model, which is here color-coded in blue, outperforms the baselines in single signal classification, signal reproduction, and behaves more human-like in the language level classification task. Although this is early work, we believe that these findings highlight the combined advantages of neuro-symbolic inductive biases, especially in generalizing in domains where there's relatively little data available. And one key extension of this work that we're currently exploring is using these models to simulate language evolution to explore the effect on different inductive biases on structure emergence. Thank you.
Right. Hello, I'm Dylan Doblar, and today I'm excited to present Noether Networks, which is joint work with Farhan, Alan, Josh, Kenji, and Chelsea. So a lot of recent success in machine learning has been due to the clever exploitation of symmetries. For example, translation invariance, permutation invariance, and rototranslational equivariance. However, there might be exploitable symmetries in problems that we care about that are either unknown or difficult to encode. For example, it might be difficult to think about how we would encode time invariance in pixel space for a pendulum system. So in this work, we ask whether we can use machine learning methods to discover these symmetries. One issue that we face is the fact that symmetries are hard to discover because they are global properties that are linked to counterfactuals. We take inspiration from Noether's theorem, which roughly states that every continuous symmetry of a system has a corresponding conservation law. And so in the example of the pendulum, time invariance corresponds with energy conservation. Nice thing about conservations is that they can be evaluated directly on raw data. So in this work, we use conservation laws as inductive biases. Consider a simple two-dimensional state space. If we're able to impose a conservation law here, we can reduce the dimensionality of our problem to a one-dimensional manifold. This makes the problem easier, and we formalize this with a set of generalization bounds where D is the dimension of the original state space, and M is the dimension of the pre-image of our actual embedding. When M is less than D, we have an improvement in this bound. We use the tailoring framework, which imposes inductive biases at prediction time, both while training and testing. And meta-tailoring is very similar, where we also adapt model parameters to perform well after we take this inner optimization step. One drawback, however, is that meta-tailoring losses must be hand-coded. So here, we aim to meta-learn these tailoring losses as useful conserved quantities. The way this looks is, given some input x naught, we use our base model to compute a sequence of predictions. We then compute embeddings and our conservation loss, which is optimized to produce tailored weights, which we in turn use to generate our final prediction. During training, we backpropagate from our task loss all the way back to our embeddings. The first setting that we explore is an ideal pendulum and spring, where we parameterize our Noether loss as a symbolic formula. And we find that our Noether network can indeed recover this functional form. In a real-world pendulum system, we also discover that Noether networks can find approximate conservation laws, and they outperform Hamiltonian neural networks, which force exact conservations. The last setting that we consider is the case of real-world video prediction, where we must predict subsequent frames, and we formulate our embedding as a two-layer CNN. Here we see that our baseline on the left exhibits artifacts, which the Noether network mitigates to some degree. With that, I'd like to thank my collaborators, and I'll take any questions offline.
Yeah. It doesn't show. It's okay? Okay. You can press that sign there. I cannot. The minus sign. I cannot. You can't, that's okay. But, yeah. Let's do the other way. option is to unplug the way. No, wait here.
Go to here. Oh yeah.
No, you really care about this.
Oh yeah. All right. Okay. Good. Hello, everyone. Today I'm presenting a state estimation algorithm. And we're considering this running example where we want the robot to dress the person with a sleeved jacket. So with the sleeve, human elbow position is occluded, but human elbow position is critical for the robot to do decision making. So in this work, we want to develop a state estimator that we can estimate the human elbow position. And yeah, so state estimator has multiple ways. One way is probabilistic approach, which will produce a point estimate and a covariance. And consistency is a very important property defined as unbiased point estimate and covariance matching the actual estimation error. And another approach of state estimation is set-based estimate. In this approach, it will produce a set at every time step that can bound the true state. And the consistency here is interpreted as a true state being bounded by the set estimate. In this work, we focus on the set-based approach. And in particular, we focus on the consistency guarantee, which means that we want the set produced by the algorithm always bound the true state of the human. And just as a motivation, as you can see here, in this video, the human is being dressed by the robot, and the human during the task will move his arm around. And so it's very hard to expect the point estimate to be perfect all the time. Therefore, in this work, we consider the set-based estimate, and we want to make the set-based estimate to be consistent. And in particular, we focus on because the system is very complicated. So we assume that our dynamic model and observation model are both learned. And we want to capture the epistemic uncertainty during this task. Therefore, we have this title site-based state estimation with probabilistic consistency guarantee under epistemic uncertainty. And so let's go back to this task. Basically, we consider state as a human elbow position and measurement as all the things that we can observe. And we model dynamic function and observation function as Gaussian process and use confidence interval to capture the epistemic uncertainty. And we combine that with zonotope-based state estimator. And the algorithm works as follows. At time t, we have a previous estimate represented as a green set. And we first propagate the green set through the dynamics learned by Gaussian process into this yellow set, which is the dynamics consistent set. And then we, given a observation, we construct a blue set, which is a measurement consistent set. So this blue set includes all the states that are consistent with the measurement. Then we do an intersection between the two sets and produce a new green set. And the intersection is a new estimate of the system. So in the end, our algorithm is able to guarantee probabilistic consistency, meaning that for all the time, the state will be bounded by the set. And in the meantime, if our algorithm omits all the uncertainties and the linearization errors, our method reduced to GP-EKF, which is a previous work, combining Gaussian process with EKF state estimator. And this is significant because our method is a set-based method and the GP-EKF is a probabilistic method. So we theoretically bridge the two type of method and show that they are equivalent in some ways. And in the end, I just want to share with the video. Basically, on the left, you see the real human. On the right, you see the simulation replaying the real data, and the green box is the set generated by the algorithm as the estimation of the human elbow position. And as you can see, even though the human moves a lot, the box will enlarge to capture the true human elbow position. And yeah, I'll take questions offline.
Okay. Hello, everyone. I'm Jay, and I'm going to present our work at this year's RSS. This is a work collaborated with Tao, Lara, Mike, Wojtek, Shen, and Pukit. Jointly optimizing morphology and control can significantly improve the task performance of a robot, such as a manipulator, for example. However, optimizing the morphology is a challenging task since it requires a general and effective parameterization for the shapes. An ideal parameterization should work for articulated robot designs with complex geometries, result in designs that can be easily manufactured, and more importantly, the parameterization is better to be differentiable to allow efficient gradient-based optimization. Previous works typically solve this representation problem by modeling each component by a primitive shape. However, those primitive shapes cannot describe the complex designs required for interesting manipulation tasks. Other choices are CAD or sign distance field parameterizations, but both of them are slow, non-differentiable, and hard to be applied to articulated robot designs. In this work, we propose a differentiable framework for robot core design. At the core of our framework is a deformation-based design parameterization and a differentiable rigid body simulation specialized for context-rich tasks. Our deformation-based parameterization is based off cage-based deformation methods. Specifically, we propose a hierarchical parameterization for articulated robot designs. Starting from a set of high-level cage parameters, our algorithm computes a coarse cage mesh, and those coarse cage mesh in turn deform the underlying mesh of each component through cage-based deformation. And from that, we can easily calculate the kinematics and dynamics parameters of the robots. And each step here is computationally efficient, analytically differentiable, and also preserving the manufacturability of the design. For a complete pipeline, we further developed a differentiable rigid body simulation for context-rich manipulation tasks. I'll skip the details here due to the limited time, but the most important feature is that our simulation is able to compute analytical gradients of the task objective with respect to all kinematics and dynamics parameters of the robot. And by combining the morphology parameterization and the simulation together, we obtain an end-to-end framework. The differentiability of each step allows us to effectively backpropagate the gradients of the loss through the whole pipeline to the morphology and control parameters. And then we can use efficient gradient-based optimization for core design. We test the efficiency of the gradient-based optimization enabled by our differentiable framework on 4 manipulated core design tasks. I illustrated one of them here. In this task, the finger is required to flip a heavy box. The video on the left shows that it's insufficient to only optimize for the control. By co-optimizing the shape and control through simple gradient-based optimization solver LBFGS, an interesting hook-like structure is evolved to hook on the back surface of the box to flip over the box more easily. We compare our method to gradient-free methods. The results show that our method is able to find better morphology and control combination while only using 10 to 20 times fewer simulation iterations. We further tested the manufacturability and functionality of our optimized designs. We 3D printed the finger components and assembled optimized design. And we conducted stress tests on the cubes of different sizes to test the functionality and robustness. And the experiment shows that the manufactured finger can successfully flip the cubes in real world. So thank you.
Our next talk will be virtual with Javier Lopez-Contreras. No? Oh, is it you? You get confused? Okay.
Is it me now or is it Yuan?
Wait, I need to come up here. Oh yeah, you're right.
Yeah. Okay, so hi everyone. My name is Yuan Gong, and today I'm going to present our work at Interspeech 2021, named Audio Spectrogram Transformer, or AST in short. So it's joint work with Yuan Zhong, James Glass, and me. So we are all from the MIT Spoken Language System Group. So we released code on GitHub if you are interested. So, so first, let me talk about the tasks. So we focus on the audio classification task, which aims to map audio waveform to a single label, for example, speaker ID, speaker emotion, voice command, background sound, sound event, so anything you want. So which means audio classification covers a wide range of tasks. But I want to say that automatic speech recognition is not part of audio classification, as it predicts a sequence of labels. So, and the system probably can work for other 1D signals like ECG, EKG, not limited to audio and speech. So conventionally, how we do this? I think after 2015, so people use a deep learning method. So they first convert the waveform to a 2D spectrogram, which the horizontal axis is time and the vertical axis is frequency. And you can see like this. And then they just fill the audio spectrogram as an image and input to a 2D convolutional neural network, like how computer vision people do their job. So for example, the convolutional neural network can be ResNet, can be efficient at anything. So, so what we do is we switch from the convolutional neural network-based model to transformer-basst model. So, namely from the CM model to the AST model. So, okay. So we have on the left side, I show a state-of-the-art CM model. So you see that a lot of components is quite complex. And on the right side, I show AST model, which is extremely simple. We only have 2 projection layers and 1 transformer encoder. So what we did is we first split spectrogram into small patches and form a sequence and input to a transformer encoder. So here we just add a potential embedding, which is learnable. So one special thing is we use ImageNet pre-train transformer encoder, which sounds weird, but it's crucial to the performance. So I don't have time to introduce how we pre-train the network using ImageNet, but you can see, check our code. So the final thing I want to discuss today is why we want to use a simple architecture rather than the CN architecture, which was very successful over the past years. So the first reason is transformer introduce plain inductive bias. So CN have stronger inductive bias such as locality and translation equivariance, while transformer is more in the philosophy of let data speak for themselves. And it has larger receptive field, which can capture long distance correlation at the first layer, which CN cannot do. And further, it has isotropic architecture, which the tensor of each layer is equal size and shape throughout the entire network. And specifically for the audio tasks, it naturally supports variability input compared to CN, which is a good point. And finally, we got best result on all tasks we evaluated. So it provides best performance. Okay, so that's all I have today. Thank you so much.
Now, yes, we have a virtual presentation.
Hi, can you hear me and see my screen? Okay, I cannot hear you.
You can see it all right. Yeah. Okay.
Yep, is everything okay?
Yep, go for it.
Okay, so hi, my name is Javier, and I'll be presenting our paper, A Large-Scale Benchmark for Few-Shot Program Induction and Synthesis, which was presented at ICML 2021. And the motivation for this paper was looking at benchmarks in meta-learning, which we saw that were naturalistic and large, but their tasks were too close together, so it was easy to reuse features. And then also looking at benchmarks in program induction, which required much broader generalization, but were smaller and manually created, so machine learning couldn't have a big impact in this field. And so what we wanted to present is a large and naturalistic few-shot learning benchmark, which also required broad generalization, and we called it progress progress dataset because it's programs that come from real executed subproblems. And how do we create this dataset? So we leverage programming competitions in which programmers have tasks consisting of a story and then some input-output examples, and then they program their solutions. And using the solutions as a benchmark is a bad idea because of two things. Firstly, because they are too difficult for program synthesizers right now, and also because there's not a lot of them. So our idea is to extract functional subcodes or subproblems from these solutions. And how do we do this? Let's see an example. So let's say we want to extract the subcode from line 13 to 17 in this bigger code that is calculating a sieve of earthostiness. What we do is we execute the state of the program. We interpret the C++ program until the beginning of our subprogram, and then we take a snapshot of the state of the program at this point, and we call this our inputs. And then we continue to execute until the end, and we take another snapshot of the state, and we call this our outputs. And then these inputs and these outputs, together with the C++ code, we can obtain a C++ function that takes some inputs and outputs some outputs, extracting test cases from the global test case. And then we clean up these test cases because there's some lines in these functions, because there's some lines in this function that are useless. For example, here, the vector v and the line 15 are useless, so we can take them out, we can slice them out. And in this way, we produce our subproblems. And then the set of all of these subproblems is what we call our data set, right? And we also add these program expression graphs, which are just a more abstract representation of the C++ functions and could be potentially can be interesting as a learning objective. If we compute some statistics on our data set, we can see that it is both naturalistic and hard to generalize. We see it is naturalistic looking at the distribution of integers in input-output. And we see here that the distribution is being very human-like. So small numbers are much more frequent than large numbers, and positive numbers are more frequent than negative numbers. And then we also see it's hard to generalize looking at the ratio of train and test. We see that there's a lot of problems in which the test executions are bigger or have a bigger ratio than what the executions looks on test. And then we also implemented a preliminary transformer baseline. And we tried different versions of this baseline, and the conclusions were two. Conclusion was that these are some encouraging numbers, because we can see here that even if we didn't do very well on our own benchmark, we still could solve some problems. The results were also consistent with our expectations that certain things should help our baseline, but still there's a big room for improvement, because the numbers are very low. As you can see here, we only make about 5% of our data set. And that's all the presentation. Thank you to all the collaborators, and I will take any questions offline as well.
Our next presenter is Joe O'Connor.
Okay. Hi, I'm going to be taking you through my work done with Jacob Andreas, in which we investigate the extent to which transformer language models can take advantage of different aspects of contextual information. Okay, so just to give a little background, we're doing language modeling here, which means our task is given some sequence of context words, try to predict the next word. There have been a variety of approaches introduced over the years, from n-gram models to RNNs and now transformers. And each of these models improved over the last. And one of the driving forces behind that improvement has been increasing the number of words in the context that the model can use to make predictions. Giving models access to longer context improves their performance as language models. Their predictions change even when you change things far away, and their predictions improve if you make context longer. So with transformers specifically, this has motivated a whole bunch of recent work designing transformers that can handle longer and longer contexts. And these approaches work. The effect continues to hold, even when increasing context sizes all the way out to tens of thousands of tokens. But what is it exactly that language models are actually getting out of these longer contexts? Is it that the long-range context is providing a source of topic information, or that it's serving as a repository of named entities for the model to condition on, or what? This is still poorly understood, and the purpose of our work is to understand it better. The way we're going to do that is the following. First, we'll train a skyline model that makes predictions given the full unaltered context window. And we'll also train a baseline model that makes predictions with the long-range context removed. Now, suppose we want to know whether, for example, word order carries information that is usable by the model in the long range. We can determine that by training a model to make predictions with the order of the words in the long-range context shuffled. If that model's performance is similar to the model with access to the full context, then word order must not carry significant usable information. And if the model's performance is similar to the model with no long-range context, that would imply that word order is a significant source of usable information for the model. So more concretely, we'll start with a chunk of text and divide it into a context and a target region. Then we'll apply an ablation, like breaking a sentence into trigrams and then shuffling them to the context. We'll train the language model to predict given the ablated context, along with our skyline and baseline models. And then we'll measure model's negative log likelihood on held out data, and we'll see where our ablated model falls on the spectrum. The closer the performance is to the skyline, the less information is removed by the ablation. And we're using GPT-2 architecture here, not pre-trained, but rather trained from scratch on Wikitext 103, which is a standard English language modeling benchmark. Okay, so our first question here is, does word order carry usable information? To test this, we do a bunch of different shuffling experiments. In this case, we're going to shuffle trigrams, preserving local but not global structure, and find that we lose only 35% of usable information in long range. So from that, we can conclude that precise word order is not very important when local co-occurrence statistics are preserved. What about word identity? If we only give the model access to a particular type of word, say nouns, will that context still be informative? The answer seems to be yes. In fact, we have this very striking result that deleting everything but nouns from the long-range context improves model performance by 9%. So in addition to all of the usable information being preserved, we actually see a performance boost, which we attribute to a reduction in overfitting. Also in this paper is a discussion of how our experimental paradigm relates to an information theoretic framework called V-information, defined by Zhu et al. 2020, more than a dozen additional ablations, test time only ablations in the style of Kondowal et al. 2018, and a preliminary investigation into how we might leverage our results to build better models. So what can we take away from all of this? Number one, long-range information is primarily captured by content words and local co-occurrence statistics, while on the other hand, based on the experiments that we haven't talked about today, things like general topic or named entity information, fine-grained syntax, global ordering of information, all contribute very little to long-range model predictions. And finally, we end with an open question. Do our findings reflect limitations of transformers, or are these fundamental information theoretic properties of English or even language in general? And that will require more investigation. Thanks for listening.
I'm Yunsheng. Yeah. Hello, everyone. My name is Zhezheng. I'm going to present our paper, Temporal and Object Quantification Networks. This is the collaboration with Jiayuan, Chuang, Josh, Zhezheng, Leslie, and Tomer. People understand actions and events by observing the relations among objects that evolve by time and apply temporal rules over them. For example, in a soccer game, we can interpret the action a player is possessing the ball as a relation between the player and the ball. The action a player is passing the ball to the other player can be possibly recognized as three sequential stages, which are a player is possessing the ball, the player kicks the ball, and the other player is possessing the ball. This understanding directly applied to past action on various soccer settings, such as soccer videos with more players, larger playground, or double speed replay. In our work, we present TOQ nets that use temporal and object quantifications to realize first-order linear temporal logic. TOQ nets can learn action concepts that generalize to different number of players, arrangements, and timing. We represent relational features with tensors. At each time point, we use a feature tensor to represent global features that doesn't involve any specific object. and a two-dimensional tensor to represent unary feature corresponding to each object. We can also represent relation of higher order, such as binary relations and ternary relations with higher dimensional tensors. The advantage of using tensors is that we can use tensor pooling operations to realize quantifiers in first order and linear temporal logic. This is the overall architecture of TOQNS. The input features are first processed by K relational reasoning layers. Next, the numerary features are fed into the temporal reasoning module with L layers to get the temporal features. Finally, the features of the trajectory are used to classify the action. Instead of constructing logic formulas explicitly, TOQNS use object and temporal quantifications, also with standard neural networks to describe actions. The entire neural network can be trained with sequence labels using backpropagation, just like other neural networks. Importantly, since all quantification are realized as tensor pooling operations, TOQNS allows the same network weight to apply to different number of entities and different lengths. We test TOQNS on Sorger dataset for action classification task. We split the 9 actions into 7 regular actions and 2 new actions. For each regular actions, there are 5,000 training samples available, where for each new action, only 50 are available. On regular actions, our model significantly outperforms other baselines by a margin of 12%. And the results on new actions suggest that our model are much more data efficient. In addition to high accuracy and data efficiency, a key feature of TOQNS is the generalization to different number of entities and against temporal warpings. We train all models on standard 6 versus 6 game where the actions are centered at the middle frame. Then we test all models on the 3 versus 3 games and 11 versus 11 game. And we also test the models on the time warped sequence where the action may take place at any time during the video instead of the middle frame. When generalizing to more or fewer plays, TOQNS experienced only around 10% performance drop, which is significantly less than all other models. And when generalizing to temporal warped sequences, TOQNS experienced almost no performance drop, compared with with baselines with temporal convolution who have up to 60% performance drop. Note that space-time and non-local baselines have also have no performance drop on time warping sequences because they are completely agnostic to temporal ordering. For more details, please refer to our project page and paper. Thanks.
Our next presentation is by Zhezheng.
Hi, should I start?
Jeff?
Should I start?
Yeah, go for it.
Oh, okay. So hi, everyone. My name is Jeff, and I'll talk about our recent effort on sparse speech processing. And this is mainly joint work with Yang from MIT IBM in my advisor Jim class. So model scaling has become an necessary ingredient for getting state-of-the-art performance, especially in the self-supervised learning paradigm in speech, such as the wave-to-back 2. And yet pre-training fine-tunings are unaffordable by many. So in our newest paper, we're looking at 2 questions. How sparse can we prune these models do, and how can we do it efficiently? And then how does sparsity affect low resource ASR performance? And then our follow-up work submitted to ICAST, we're mainly pruning TTS model, and surprisingly, there hasn't been any work on pruning TTS models either. So in this work, we're mainly interested in how sparsities affect speech perception. The tools that we're going to use is based on unstructured magnitude pruning, which is widely adopted in the vision community. So weights and neural networks are removed based on the magnitude. And this is usually target task, or in our case, target language dependent. So for example, wave-to-back 2 fine-tuned for French, and then we prune it and then do some network retraining. one surprising observation is that models fine-tuned for different spoken languages have high similarity in their pruning patterns. So for example, Wavedirect 2.0 fine-tuned for French and fine-tuned for Spanish have 97% in their pruning mask overlap. And this holds for any spoken language pair, any model scale, amount of supervision, and sparsity level. This inspires us to make a small modification to existing pruning methods, which we term prune, adjust, reprune PARP. And PARP is extremely simple, only consists of 2 steps. So in the first step, we prune without any task information. So let's say our target language is Spanish. We can prune with French, Swedish, etc. to get an initial sum network. According to the observation in the previous slide, because of the high similarity, the initial sum network and the target sum network have high similarity. We only need to do a slight adjustment in the second step to avoid pruning out the important weights in the pre-trained initialization. The main experiment setup is on low resource ASR, and this is the English ASR setup. And this is the standard setup adopted by many. We see that the black line is PARP and it outperforms the baseline pruning methods. And surprisingly, applying PARP in the extreme low resource condition with 10-minute of pair data can give us performance boosts over the full model, which is not seen in, with other pruning methods. And we have results for multilingual ASR. This is on French. We also have results under spoken languages. One last interesting experiment we did is Cross-Lingual mass transfer, where PARP allows us to do efficient adaptation of the sum network from a different spoken language to the target spoken language. For example, we can take model fine-tuned for Swedish, prune it to get the initial sum network for Swedish. And then PARP step 2 is allows us to efficiently adapt the Swedish sum network to, for example, Spanish. And doing this, there's no error rate reduction as shown on the right. And our follow-up work is on looking at naturalness, intelligibility, and prosody when there's sparsities in the models. And this is my presentation. If you have any question, feel free to talk to me. Thank you.
Right? Mm-hmm. Hi, I'm Aviv, and this is work we did on physically grounded social interactions. Imagine you're helping your friend move, and in one case he has a big box, and in the other he has 2 small boxes. So helping him would look different in the context of different physical environments. And in this work, we were interested in making inferences about helping in different physical environments. So we've built a data set for social interactions, and we provided baselines and a model of our own for making such inferences. We'll start with an example. In this case, the agent's goal is putting the box somewhere, and his friend has a goal of helping him. Both agents are taking actions in the environment to avoid bad outcomes like the box falling down. And in the same way that we can make these inferences in the real world, we can also do that in simulated environments. And this is the environment in which we build our data set phase. We also have agents, objects, locations, and walls like in the real world. And agents have a field of view, and they can take actions to achieve their goals. Each agent has a physical goal, which can be putting an object on a landmark, approaching another agent, or getting to a landmark. And they can also have social goals, and the social goals define the relation between them. For example, if an agent has a social goal of helping, the relation would be friendly. And if an agent has a social goal of hindering, the relation would be adversarial. If each agent has a separate physical goal that's unrelated, we'd say the relation is neutral. To procedurally generate this data, we first provide the physical configuration of the environment, for example, the size of the agents. And we also provide the abstract configurations, the goals and the relations. So we give the physical and abstract configurations and the agent observations to a planner. which provides us with actions for the agents. We then simulate those actions with the physics engine, get the next step, update our observations. And we continue to do that to get each clip. And each clip is about 10 to 25 seconds long. And we get a rich set of social interactions based on the different combinations we have of the physical and abstract configurations of the environment. We provide 3 benchmarks on this data set. The first is for recognizing the physical and social goals of the agents. The second is for recognizing the relationship between them, friendly, adversarial, neutral. And the third is forecasting the next 10 steps given a partial video. We compare to state-of-the-art methods for extracting relations between agents that are either LSTM or graph neural net based. And these baselines are bottom-up, meaning they go from trajectories to predictions. And we suggest a model that also has bottom-up components, but also has top-down components. And we think that's what makes the difference. So we go from observed trajectories to environment configurations. And then using our planner, we estimate trajectories from those predictions. Then we compare estimated trajectories to the observed ones. And based on the discrepancies between them, we can improve our prediction of the environment configurations. We continue this process iteratively until we get a final estimation. On the 3 tasks that we propose, goal and relation recognition and trajectory forecasting, our model in red does better than the baselines we compared to. To conclude, our dataset combines physical scene understanding and social scene understanding. And we provided a baseline and a model of our own for making inferences about social interactions in our dataset, but we also encourage other people to try out their own model. Thanks.